Hello, everybody. Let's go over some questions from Unit 2 and then some Unit 1 Module 4 questions where we talk about light-matter interactions, absorption and emission spectroscopy, and the bond, and so forth. All right, let's start with this question over here. We are given a mass spectrum. A diethyl glycol is one of the substances that is emitted via second-hand smoke. Based on the structure and mass spectrum, what is the most likely structure of the most abundant fragment at this particular mass? Okay, mass at 45. So now it's true that we cannot see the mass spectrum properly over here. But if we could say it, then we should see that this highest peak is for 45. But anyway, it is not relevant to this question anyway. So the idea is the mass of the fragment is 45. Now, in other words, whatever this fragment should have a mass of 45. If you look at the first one over here, we have 2 carbon atoms. Okay, this is a carbon, and then we have 2 hydrogens bound to it. There may be 2 hydrogens over here as well. Okay, and if you add them up, you have we have 1, 2, 3, 4, 5 hydrogens. So 5 times 1 plus 16 for oxygen, and then we have 2 carbons. So it is 2 times 12. Okay, if you add this up, then you're gonna get 5 plus 16 plus 24. Which is gonna be 30, 40, 45 over here. Okay, which is exactly the mass we have. Now, if you go to something else, see, we picked the answer up already in the first one. So, but anyway, let's see that. Right now, we see that the first fragment mass matches with 45. So that's the best answer so far. If you look at the other answer over here, we have 2 carbons, that is 2 times, actually, 3 carbons. There's another carbon over here as well. Okay, there's 3 carbons, 3 times 12, which is 36. Plus we have 2 oxygens, that is 2 times 16, which is 32. 32 plus 36 alone is 68, right? Which is over 45. Therefore, option B cannot be our answer. And then moving on to option C, we have 2 carbons, that is 2 times 12, in option C. And then we have 2 oxygens, that is 2 times 16. Okay, if you think about this, 2 times 12 is 24, plus 2 times 16 is 32. Without even considering hydrogens, you see that 32 plus 24 is 56, which is more than 45. Therefore, that is out as well. Now, in our option D, we see that we have 1, 2, 3, 4 carbons, 4 times 12, which is 48. Okay, and plus we have 16, and plus we have hydrogens. Okay, so 4 times 12 is 48 already. Therefore, which is more than 45. Therefore, option B cannot be our answer. Therefore, the correct answer is option A. Okay, now that's how we do that problem. Okay, so the correct answer is this guy over here, which has a mass of 45 in atomic mass units. Okay. Moving on to the next question. Okay, there has been a rising concern of electronic cigarettes causing permanent lung damage, and one of the substances that is present in these devices is known to cause lung cancer or lung disease. This substance is found to have these percentages of carbon, hydrogen, and oxygen, and its mass spectrum is shown to the right. What is the molecular formula of this compound? All right. Now we see that this particular compound has a molar mass of this compound is given by the molecular ion pick, which is right over here. We see that that is between, let's say, we have 20 here, 20, 1, 2, 3, 4. So each line is 5. So this should be 85, something around 86 grams per mole should be your molar mass. Now, if you look at the options we have here, definitely if you consider something like this without doing any calculations so far, we can see that option D does not match with this, because we have in option D 2 carbons, 3 hydrogens plus 1 oxygen. If we add this up, 2 times 12 is 24, 24 plus 3 is 27, 27 plus 16 is 43, which is like half of it. So this is invalid. Option D is out. And then twice of that, which is C4H6 and O2. So this is 43, right? Twice of this is 46. I mean 86. Now we see that the option B is twice of that. Okay, that means this should have a molar mass of 86. Let's do that. Okay, we have 4 times 12 times 6 times 1 plus 2 times 16. 4 times 12 is 48. 48 plus 6 is 54. 54 plus 32 is 86, which matches with our answer. Okay, without even doing any calculations. Okay, now anyway, let's consider the other 2 options as well. When it comes to option A, we see that it has 2 more hydrogens than option B. That means this is 86. Okay, this has a mass of 86. This must have a mass of 88, which does not match with our molar mass from the mass spectrum. And then therefore I'm going to eliminate that as well. And then when it comes to C3H6O3, let's count that actually. So we have 3 times 12, I'm talking about option C now, plus 6 times 1 plus 3 times 16. So if you add this up, 3 times 12 is 36. 36 plus 6 is 42. 42 plus 3 times 16 is 48. 42 plus 48 is 90. So this is going to add up to 90. And that is out as well. Okay, without even considering the elemental analysis data, which is over here. Okay, now currently our answer is this. All right, this is what I would go with. I mean, I'm just by eliminating all the wrong answers. The other way of approaching this question is maybe the algorithmic way of approaching this here is we know that when it comes to carbon in this compound, 86 is the mass of the entire compound, but 55.8% is the mass of carbon. Okay, if you divide that by the molar mass of carbon, which is 12 grams per mole, you're going to get the moles of carbon. And if you do that calculation, you're going to see that 86 times 55.8 divided by 100 and divided by 12 is around 3.99, or is about 4. Okay, so that immediately cancels out option C and D. Okay, and then we just need to do hydrogen now. If we do hydrogen the same way, we see that hydrogen percentage is 7%. That means 86 is the entire mass of the compound, of 1 mole of compound, and then 7% of that mass is the mass of hydrogen, and divide that by the molar mass of hydrogen, which is 1 gram per mole. You're going to get the number of moles of hydrogen. And if you do that, you're going to get 86 times 7 divided by 100 and divided by 1, and you're going to get around 6. about 6. Okay, so that's going to eliminate option A. So we're going to be left with option B. That's the other way of handling this problem. Okay, moving on to the next question. Okay. Right, let's take a picture here. Right, now in this question you are told that 2-furaldehyde has the absorption spectrum shown to the right. Okay, and then which of the following energy diagrams best reflect the two major absorbance wavelength of 92 and 110? First of all, these are absorption spectra. In absorption spectra, you're going from the ground state to high energy levels. Okay, for that reason, I'm going to eliminate options A and B, because A and B show that we are going from a high energy level to a low energy level, which is characteristic of emission, not absorption. Okay. And then we are between option C and D now. And when it comes to the first peak over here, indicated by 1, it has a lower wavelength. Shorter wavelength means higher energy. And that means that should the transition 1 or the peak 1 should correspond to a higher energy transition. Okay, so if you look at option C and D, in only D, we have a higher energy transition for 1. That means that compound is absorbing a higher energy photon to go from the ground state to a high energy level. Okay, because this energy gap needs to match with the photon that is absorbed, and therefore the high energy photon should match with 1. So therefore, transition 1 or the peak 1 goes with this, and the peak 2, which has a longer wavelength, that means lower energy. How do we know that? Energy is equal to hc over lambda. Energy and the wavelength are inversely proportional to each other. Okay, so longer wavelength means lower energy. So the transition 2, a low energy photon is absorbed because the energy gap is smaller, and that is corresponding to this guy over here. Therefore, the correct answer is option D. Okay. Moving on to the next question, the UV visible spectrum for this molecule is shown in question 10. What type of transition is this spectrum representing? You're already told that this is UV visible spectrum. UV and visible light affect electronic transitions or induce electronic transitions in the molecules. Therefore, the correct answer is option A. Okay, moving on to the next question. Question 15. Okay. No. Right. Phenol is a common substance found in electronic cigarettes, the UV visible and infrared spectra. This is infrared, and this is UV vis. Okay, how do we know? Yes, the name UV vis, infrared. Okay, are shown to the right. Which waves below best depict the light required to induce the 3 transitions shown? 3 transitions indicated. Okay, so the first transition is in the IR range. Okay, so IR has a lower energy than the visible because the last light in the visible range is red. Okay, so which has 700 nanometers. So this is V. This is 700. This is 400 nanometers. So infrared radiation has longer wavelength than red light. Okay, that means lower energy. Okay, so longer wavelength, and then that means 1 should be the longest wavelength, and for that reason we can eliminate option C and option D because they have a shorter wavelength for option 1, wavelength 1 there, and therefore those 2 are out. And then we need to look at the visible spectrum. Visible spectrum 2 has a shorter wavelength. okay, around 200 nanometers, so something like that. And then 3 has a longer wavelength, with it something close to 270 nanometers. So, so the shortest wavelength must be 2. So between A and B, the shortest wavelength is assigned to 2 in option B. Therefore, the correct answer is option B. Okay, that is how we do that. Moving on. Okay. Lead is one of the metals found in cigarettes that can be detected by its distinct emission wavelengths. If lead has a strong emission wavelength at 405.7 nanometers, what is the energy of that light in kilojoules per mole? Okay, so again, energy of light or energy of photon is given by energy is equal to hc over lambda. And then H is 6.626 times 10 to the power of minus 34 joules seconds. And C is the speed of light, which is 3 times to the power of 8 meters per second. And divide this by the wavelength, which is given to us as 405.7 nanometers. But speed of light is in meters. The wavelength is in nanometers, but they need to match, or else I use them in the same equations. So I'm going to convert nanometers to meters by multiplying that by 10 to the power of minus 9, because that's how many meters you have in a nanometer. And when you do that, nanometers cancel out, meters cancel out, seconds cancel out. You're going to get the answer in joules. Okay. And then, yeah, if you do that roughly over here, I don't have, let me see, if you use a calculator at this point, what I can do is I have 6.626 multiplied by 3 and divided by 405.7 gives us 0.0489. Okay, let's say 49 times now the exponents of 10. Okay, so 10 to the power of minus 34 times 10 to the power of 8 is 10 to the power of minus 26, and 10 to the power of minus 26 divided by 10 to the power of minus 9 is 10 to the power of minus 17 joules. Okay, this is like 4.9 times 10 to the power of minus 19 joules per photon. But they're asking the energy of 1 mole of photon. To do that, this is in joules, you multiply this by the Avogadro's number, which is 6.022 times 10 to the power of 23, because that's how many photons you have in a mole, and divide this by 1000 or 10 to the power of 3, because that's how many joules we have in a kilojoule. And then now you see that joules cancel out, and then you're going to get the answer in kilojoules per mole. And then if you do this calculation, you see that you know what, let's do the exponents here. You know what, you can just calculate that. All right, let's multiply by the Avogadro's number, 6.0022, and then you're gonna get 0.295, let's see, 0.295 in okay, before the exponents, and now the exponents. Okay, 10 to the power of minus 17 times 10 to the power of 10 to the power of 23 is 10 to the power of 6, and then 10 to the power of 6 divided by 10 to the power of 3 is 10 to the power of 3, and then that means this is about 295 kilojoules per mole. That's your answer. This is about, right? And then that is not option A, it's not option B, D, and that is our option C, and that's your correct answer. All right, so that's how we do that calculation. Moving on to the next question. Okay. All right. Lead also has some less intense emissions at wavelength of this. What is the frequency of radiation? Now, what we have here is the wavelength, and then you have to calculate the frequency of that. And we know the frequency, or we call it nu, is equal to c over lambda. Okay, and then if you just plug and chuck the numbers here, c is the speed of light, which is about 3 times 10 to the power of 8 meters per second, and divide this by the wavelength, which is 283.3 nanometers, but we need this in meters. To do that, we would multiply this by 10 to the power of -9, because that's how many meters we have in a nanometer. And we see that nanometers cancel out, meters cancel out. You're going to get the answer in per seconds or in hertz. And if we just do the exponents here again, like last time, we have 3 divided by 283.3, and the exponents, when you divide 10 to the power of 8 by 10 to the power of -9, you're gonna get 10 to the power of plus 17 per second. Okay, so that's a large number, which is definitely larger than option D, definitely larger than option C as well, and definitely larger than option A. It's -19. So the only option remaining is this number over here. You can even plug and chuck the numbers and see whether we have the correct number. 3 divided by 283.3 is 0.0106 times 10 to the power of 17, and this is per second, and this is equal to 1.06 times 10 to the power of 15 per seconds or hertz. Okay, so that's the answer, which is option B. All right, moving on to the next question. Lithium, a metal found in batteries of vaping devices, has 2 isotopes. Okay, which of these isotopes is most prevalent in nature? Okay, now it's not essential for this, but just to make sure that we understand this. So if we took a mass spectrum of lithium, if there are only 2 isotopes, all right, that means you're going to see something like this. Okay, this is, let's say this is the percent abundance, and then this is the mass to charge ratio. Okay, you will see 2 peaks. Okay, one at 6 and another one at 7. Okay, I don't know the heights of this yet, but we'll worry about that later. So we're going to see 2 peaks if there are only 2 isotopes. Okay. And now what we do is, if we go to the periodic table, I think there's a periodic table. Okay. Yeah, let's come back to this. Okay. All right, here's the periodic table. You see that lithium is the 3rd one over here. It's not that clear actually. So lithium is over in the first element in the 2nd period. Okay, let me have another periodic table which is clear. Okay, periodic table, and okay, here we go. We see that in the periodic table, lithium has a relative atomic mass of 6.941, if I'm saying this correctly. Okay, so that means the average relative atomic mass of lithium is closer to 7. Okay, so that tells us that you should have more of lithium 7 than lithium 6 isotope. Okay, so for that reason, if they cannot be both equivalent, if they're equivalent, equal, equally prevalent, then you should have a relative atomic mass closer to 6.5. This is way closer to 7, 6.94. That means you have way more of 7 compared to 6. Therefore, the correct answer is option A. Yeah, we have enough information, and they both actually pronounce it's incorrect, not lithium 6, lithium 7. All right, that is that. And let's do this question. Okay. An emission spectrum for cadmium is shown to the right, or shown above. Rank the emission transitions from highest to lowest energy. All right, so again, the energy, okay, energy is equal to HC over lambda, right? That means energy and the wavelength are inversely proportional to each other. So what this tells is the longer wavelength should have a smaller energy, and the shorter wavelength has a higher energy. So we have the shortest wavelength for 4, therefore this should be the highest energy, and then we have the longest wavelength for 1, therefore this should be the lowest energy. Okay, so all right, so we have the 1, 2, 3. If you look at option A over here, highest energy for the fourth one, then 3, then 2, then 1 is the lowest. It seems to be correct, so I would go with option A. And C is out, B is out, and then it comes to option D. The first and the last one are okay, but it's kind of jumbled in the middle. I mean, swapped in the middle, so therefore that is out as well. So option A is the correct answer. And then moving on, a substance commonly found in electron cigarettes has the molecular formula of this, and its infrared and mass spectrum are shown to the right. Draw the structure of the molecule. Okay. Now I think you're supposed to be given the given the bonds you have here, which is unfortunate, which is not which is not apparent here. Well, anyway, so according to what we are saying, we have a fragment at CH at 15, means we have a CH3, and then we know the molecular formula as well. So that means we have that, and I believe this is 1800. Let's say that we have C-double-bond-O bonds, and then we have some peaks over here which is relevant to CO bond, and then we have some CH as well, and then we have some, I believe we have some OH. All right, let's go with this because I mean I don't have the information, all the information I need. But let's see. So the molar mass of the compound is this much. It's not actually that much useful because you already have the molecular formula. Let's make sure that we have these fragments, like these bonds in our molecule at least. Okay, to come up with something. So we have carbon, and then what we can do is, I'll draw a possibility. You have 4 carbons, and then C-double-bond-O, C-double-bond-O, and then say OH, OH, hydrogen, 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 and hydrogen. 6 hydrogens. No, I have more oxygens than I need here. Actually, so this cannot be the answer. We only have 2 oxygens, so I didn't notice that before. So let's say that we have 1, 2, 3, 4, double bond O, OH, hydrogen, hydrogen. So we have 1, 2, 3. And then if we have a double bond over here, then there's 1 hydrogen, hydrogen, hydrogen. Let's see if we count the hydrogens now. We have 6 hydrogens, 1, 2, 3, 4 carbons, and 2 oxygens. So the number of composition match. And then the OH is there. Then therefore it says that we have C double bond, C bonds as well, if this is the case. Okay. So assuming that we have OH bond, C double bond, C bond, and CH bond, C double bond, O, C, O bonds, and this molar mass, I think this structure would do it. And then draw the fragment that would correspond, that will yield the peak at 15. So usually, I mean, the peak at 15 is for a methyl group. That tells us that there's something wrong with the structure. So let's draw another one with a methyl group. Okay, so let's do it separately one more time. Okay, this time with a methyl group. So I'm going to draw, here's a methyl group. Right, here's a carbon, carbon, OH. Then we have hydrogen, hydrogen here. Here you go. Now, if the molecule fragments from here, then it's going to give a CH3 fragment, which has a mass of 15 in atomic mass units. Okay, and the rest match as well, like the 4 carbons, 6 hydrogens, and 2 oxygens will match as well. I'll go with that based on this information, because unfortunately the information about the bonding is not here. Okay, so that's all the questions I have here. I hope this helped. I'll see you guys in class. Bye everybody.